Section: Introduction. We're here to talk about the latest advancements in language models, such as GPT-4, PaLM, and Llama. These models have pushed the boundaries of what we can do with natural language processing and generation. They can do everything from writing Shakespearean sonnets about hedgehogs to summarizing complex medical reports and solving programming puzzles. However, they're not perfect and can sometimes produce inaccurate or misleading results. As these models become more affordable to use, we're exploring ways to improve their accuracy and robustness. In this study, we're introducing a new method called meta-prompting. This technique helps a language model break down complex tasks into smaller, manageable parts. It then assigns these parts to specialized, expert models with clear and detailed instructions. The language model oversees the communication between these expert models and applies its own critical thinking and reasoning skills throughout the process. When given a task, the language model acts like a conductor, guiding the expert models and creating a narrative of their responses. The language model is responsible for choosing the experts and giving them specific instructions. But it also acts as these experts, generating outputs based on the expertise and information chosen by the conductor for each task. This allows a single language model to maintain a coherent line of reasoning while also tapping into a variety of expert roles. Our meta-prompting technique combines and expands upon various prompting ideas introduced by recent studies. It's task-agnostic, meaning it uses the same set of high-level instructions across various tasks and inputs. This is particularly useful for users who might find it difficult to provide detailed examples or specific guidance for every distinct task. For example, if a user asks the model to write a Shakespearean sonnet about selfies, they wouldn't need to provide examples of high-quality neoclassical poems. The meta-prompting approach makes language models more useful by offering a broad, flexible framework without compromising on specificity or relevance. We've also added the ability to invoke a Python interpreter to our system, which allows for an even more dynamic and comprehensive application of the technique. This extends its potential to address a wide array of tasks and queries effectively. In our experiments, we primarily used GPT-4 as the foundational language model. We compared the effectiveness of meta-prompting against other task-agnostic scaffolding methods. Our results showed that meta-prompting not only improves overall performance but often leads to the best results across a diverse range of tasks. The conductor model can call upon expert models, which are essentially itself with new instructions, to perform a variety of functions. These might include critiquing earlier outputs, selecting specific personas for certain tasks, refining generated content, and ensuring that the final outputs meet the desired criteria in both substance and form. Our main contribution in this work is the introduction of a task-agnostic scaffolding system that uses a single language model. This model not only carries forward the thread of the task but also dynamically selects and instructs expert models appropriate for each specific task. We've demonstrated the effectiveness of this system across various benchmarks, including the Game of 24, Checkmate in 1 from the Big Bench suite, and our novel task of Shakespearean sonnet writing. Our results highlight the versatility and robustness of meta-prompting in enhancing language model performance. Section Summary. The introduction discusses the limitations of large-scale language models, LMs, and proposes a new technique called meta-prompting to enhance their accuracy and robustness. Meta-prompting involves using a high-level prompt to break down complex tasks into smaller pieces and assign them to specialized expert models. The LM serves as a conductor, generating a narrative by incorporating responses from these experts, resulting in more accurate and reliable outputs. The meta-prompting approach is task-agnostic and can be applied across various tasks without the need for specific instructions or examples. Additionally, the introduction highlights the versatility of meta-prompting by demonstrating its integration with a Python interpreter and its effectiveness in achieving state-of-the-art results across different benchmarks. Section: Meta-prompting. Let's simplify and paraphrase the given text. The concept of meta-prompting is similar to conducting an orchestra. Just as a conductor brings together the unique talents of each musician to create a beautiful symphony, Meta-prompting uses a central model, known as the meta-model, to coordinate and combine the outputs of multiple specialized models, or experts, to solve complex tasks. These experts can take various forms, such as a language model fine-tuned for a specific task, a specialized tool designed to handle certain types of queries, or even computational tools like calculators or code interpreters. However, they all operate under the guidance of the meta-model. In our setup, these experts can only be called upon by the meta-model and they don't interact with each other directly. This is done to simplify the communication process and to keep the meta-model at the heart of the operation. Before we dive into the details of meta-prompting, let's clarify some terms and symbols. We use the symbol for number 4 to represent a set of finite strings, with number 5 standing for an empty string. The symbol number 6 refers to a query, which could be a task or problem described in natural language. We also have a fixed language model, symbolized as number 7, which takes an input text, represented by number 8, and produces a corresponding output. We use specific template functions, denoted as number 9 init, number 10 mid, and number 11 express, to format the input and output texts. Additionally, we have two string extractors, number 12 xp and number 12 ret, which are used to retrieve a substring enclosed within specific delimiters. The symbol number 13 represents string concatenation. Lastly, we have a specific string, error number 14, which is used to indicate an error message in the process. Now, let's look at the steps involved in meta-prompting. 1. Transforming the input. We use a transformation function, number 16, to format the raw query and provide initial instructions to the meta-model. 2. Loop iteration. The meta-model uses the current message list, number 17, to decide its next action, either answering the query directly or consulting an expert. 3. Engaging domain-specific expert models. If the meta-model can't provide an answer, it can call upon an expert and give it instructions. Each expert only sees what the meta-model shares with them and responds accordingly. 4. Returning the final response. If the meta-model's response contains a final answer, the solution is extracted and returned. 5. Error handling. If the model's response doesn't contain a final answer or a call to an expert, an error message is added to the message list. In our setup, we use the same language model, such as GPT-4, for both the meta-model and the expert models. Their roles are distinguished by the instructions given in their prompts. Section summary. The meta-prompting approach involves using a single meta-model to coordinate and combine the responses of multiple specialized models or experts. These experts can be language models, APIs, calculators, or other computational tools. The meta-model acts as a conductor, harmonizing the insights from the experts to provide accurate and comprehensive solutions. The process involves transforming the input query, prompting the meta-model, engaging domain-specific experts if needed, and returning the final response. Both the meta-model and the expert models are based on the same language model, such as GPT-4, but their roles are distinguished by their prompts and instructions. Section: Experimental Setup. In our experiment, we compared our method, called meta-prompting, with other prompting methods that don't require any prior knowledge about the task. These methods include: 1. Standard prompting. This is the simplest method where a language model, LM, is asked to provide an answer without any specific examples or additional instructions, apart from the task description already included in the question. 2. Zero-shot caught prompting. This method adds the phrase, "Let's think step by step," to the question, encouraging the model to think more carefully and iteratively before addressing the problem. 3. Expert prompting. This method uses a two-step process. First, it creates an expert identity that matches the context of the question. Then, it incorporates this expert profile into the question to generate a knowledgeable and authoritative response. We tested two versions of expert prompting: static, which uses a fixed expert description, and dynamic, which designs a new expert identity for each question. 4. Multi-persona prompting. Also known as solo performance prompting, this method instructs the LM to propose a small group of personas to address the task. Let these personas engage in a collective dialogue, generating potential solutions and refining their answers. And finally, combine all the information and deliver a final response. To test the effectiveness of our meta-prompting method, we used a variety of tasks and datasets that require different levels of mathematical and algorithmic reasoning, specialized knowledge, and creative writing. These include 1. The game of 24, where the goal is to form an arithmetic expression that equals 24 using each of 4 given numbers exactly once. 2. 3 big bench hard tasks, namely, geometric shapes, multi-step arithmetic 2, and word sorting, as well as 1 reasoning task directly obtained from the Big Bench suite, called Checkmate in 1. 3. Python programming puzzles, a collection of challenging programming puzzles written in Python. 4. Multilingual grade school math, a multilingual version of the GSM-8K dataset with translations of a subset of examples into 10 diverse languages, including Bengali, Japanese, and Swahili. 5. Shakespearean sonnet writing, a new task we created where the goal is to write a sonnet with a strict rhyme scheme and containing 3 provided words. In our meta-prompting method, the system instruction encourages the meta model to present its final answer in a specific format. This format, designed for clear and unambiguous extraction, requires that the final answer is enclosed within triple quotes and preceded by a distinct marker, final answer. Once the final answer is extracted from the model and properly post-processed, we also need to evaluate its correctness. Because we consider a wide range of tasks, there is not a single metric that allows us to measure accuracy across all. Depending on the task, we measure accuracy using one of the following 3 metrics. 1. Exact match, M. This strict metric determines the correctness of an answer by its exact match with the correct labels. An answer is correct only if it is identical to a provided reference. 2. Soft match, SM. This metric is more lenient than M. For an answer to be correct, it is enough for a correct label to be present within the model's output, regardless of any additional text. 3. Functionally correct, FC. This metric checks whether the answer is functionally correct, meaning that it follows task-specific constraints. In our main experiments, we focused on GPT-4, which is available through Microsoft's Azure OpenAI service. In addition, in our supplementary experiments, we included GPT 3.5. Both GPT 3.5 and GPT-4 are models fine-tuned for following instructions, though GPT-4 has shown significantly better reasoning and content generation abilities than GPT 3.5. In all of our experiments, we consistently applied the same parameters and system instructions to the meta model. We set the temperature value at 0, the top p-value at 19, and the maximum token count at 20. Section summary. In the experimental setup, we compare our meta-prompting approach with several baselines: standard prompting, zero-shot COT prompting, expert prompting, static and dynamic versions, and multi-persona prompting. We evaluate these methods on various tasks and datasets that require mathematical reasoning, domain-specific knowledge, and creative writing skills. To extract and evaluate the answers, we use a specific format and different metrics depending on the task. We primarily focus on GPT-4 for our experiments, but also include GPT 3.5 in supplementary experiments. Section: Main results and discussion. Our research findings, as shown in the table, reveal that our meta-prompting technique is significantly more effective than traditional zero-shot prompting methods. When we examine the overall results across all tasks, we see a clear improvement in accuracy with meta-prompting, particularly when it's combined with a Python interpreter. To be specific, meta-prompting surpasses standard prompting by 17.1%, dynamic prompting by 17.3%, and multi-persona prompting by 15.2%. Let's now explore 4 main insights that we've gathered from our data analysis. Firstly, the overall performance. Our meta-prompting method, especially when paired with a Python interpreter, consistently outperforms the usual zero-shot prompting across a variety of tasks. This method is particularly effective for tasks that heavily rely on heuristic or iterative problem-solving strategies. For instance, in the Game of 24 challenge, we observed an accuracy improvement of over 60% compared to the basic standard prompting method. We also saw about a 15% increase in Python programming puzzles, and nearly an 18% increase in accuracy for sonnet writing. These tasks require complex, iterative, and heuristic search strategies, where traditional single-shot prompting falls short. On the other hand, meta-prompting uses the collective intelligence of various expert personas to iteratively work towards a solution, creating a more dynamic and effective problem-solving environment. Furthermore, meta-prompting also proves to be effective in creative writing tasks. For example, in the Shakespearean sonnet writing task, which requires linguistic precision and creative adherence to specific poetic structures, meta-prompting significantly improves performance. While standard prompting methods achieve a 62% accuracy rate, meta-prompting reaches 79.6% and 77.6% accuracy, with and without a Python interpreter, respectively. In tasks like MGSM and geometric shapes, the benefits of meta-prompting over other prompting methods seem minimal at first glance. However, meta-prompting does provide 4 to 6% gains in Bengali and Telugu, 2 underrepresented languages with the lowest baseline performances. In geometric shapes, we expected GPT-4 to identify the shapes of objects by generating and executing appropriate codes under meta-prompting, but this did not happen. Meta-prompting only resulted in a modest 2.4% gain in this geometric task. We do acknowledge that the zero-shot COT baseline performed surprisingly better than all other methods, outperforming meta-prompting with a 10% accuracy gap. Despite the most significant gains being observed using a Python interpreter, we note that for the checkmate in one task, meta-prompting achieved a 20.8% gain even without it. Overall, our results highlight the versatility of meta-prompting and underscore its potential for broad application beyond strictly computational problems. Secondly, the zero-shot decomposition, error detection, and aggregation. The success of our meta-prompting framework is partly due to its strategic use of specialized knowledge, self-collaboration, and implicit verification loops. This method, as well as multi-persona prompting, encourages multi-turn interactions where different personas collaborate to solve a problem. To illustrate how the framework can be beneficial, consider solving multilingual arithmetic problems from the MGSM dataset. GPT-4, under the meta-prompting method, typically follows a 3-phase approach, initially translating the problem from the source language, e.g., Bengali, to English, then applying computational expertise, like calling an expert mathematician, to find a solution, and finally, conducting an independent or corroborated verification. This unsupervised approach aligns with the multilingual COT prompting method used for MGSM, where the prompt instructs the LM to first translate the problem and then solve it. Meta-prompting performs such translation without explicitly being instructed to do so. Our structured approach embodies the principle of the wisdom of the crowd, which posits that a collective opinion of a diverse set of critical thinkers often surpasses the insights of individual experts. By harnessing an ensemble of specialized expert models under the guidance of the meta-model, each contributing from different angles of expertise, we achieve more accurate and reliable problem solving. Thirdly, the concept of fresh eyes. This concept helps to address the well-known issue of LMs doubling down on their mistakes and exhibiting overconfidence. Fresh eyes are a key differentiator between meta-prompting and multi-persona prompting, and thus comparing experimental results demonstrates the advantage. In meta-prompting, fresh perspectives are introduced by engaging experts, or personas, to reassess the problem. This approach provides an opportunity for novel insights and the potential discovery of previously unnoticed incorrect solutions. Grounded in principles from cognitive psychology, fresh perspectives can lead to more creative problem solving and error detection. When individuals or models approach a problem without preconceived notions, they are more likely to consider alternative solutions and identify errors that might have been overlooked. Fresh eyes may help avoid cognitive biases such as anchoring, confirmation bias, as well as overconfidence. Consider the following summary of an execution, which illustrates the benefit of fresh eyes in practice. Say the task is the 24 game, e.g., to use each of the numbers 6, 11, 12, and 13, exactly once, in an arithmetic expression whose value is 24. The history may look something like the following. The meta-model proposes consulting experts in mathematics, problem solving, and Python programming. It emphasizes the need for accuracy and adherence to constraints, suggesting the involvement of another expert for review if needed. An expert proposes a solution, which a second expert identifies to be incorrect, and the meta-model suggests writing a Python program to find a valid solution. A programming expert is consulted to write a program. Another programming expert identifies an error in the script, modifies it, and then executes the revised script. A mathematics expert is consulted to verify the solution output by the program. After this verification, the meta-model outputs it as the final answer. This example underscores how meta-prompting, incorporating fresh perspectives at each step, since the expert's prompt does not include the whole history, not only finds solutions but also effectively identifies and corrects errors. The diversity of perspectives, ranging from problem-solving strategies to technical execution and verification, demonstrates how different angles of expertise contribute to a more robust and reliable problem-solving process. Section Summary. The results of our experiments show that our meta-prompting approach is more effective than standard zero-shot prompting methods, with notable increases in accuracy across various tasks. Meta-prompting leverages the collective intelligence of expert personas to tackle complex problems and is particularly effective in tasks that require heuristic problem-solving strategies. Additionally, the success of meta-prompting lies in its use of specialized knowledge, self-collaboration, and fresh perspectives, which help identify errors and improve problem-solving accuracy. Section: Real-time code execution. Let's discuss the real-time execution of code. We've made a significant leap forward in solving algorithmic problems by incorporating a Python expert for code generation and execution into our meta-prompting framework. This is clearly seen in Python programming puzzles, where the success rate jumped from 32.7% to 45.8% thanks to the integration of the Python expert. This increase is mainly due to the meta-model's ability to generate and execute code based on natural language instructions. Real-time code execution allows for immediate validation and optimization of solutions, greatly enhancing problem-solving efficiency and accuracy. This improvement isn't limited to just one type of task. In tasks like the game of 24 and word sorting, accuracy rates rose by 56.0% and 15.6% respectively when a Python interpreter was integrated into the meta-prompting. Compared to the baseline standard prompting, these accuracy gains correspond to 64.0% and 19.2% respectively. These improvements underscore the importance of code generation and execution in boosting the effectiveness of the meta-prompting framework, showing its transformative impact across various computational tasks. On average, integrating a Python interpreter results in an additional performance improvement of 11.5% across different tasks compared to meta-prompting without a Python interpreter. However, introducing real-time code execution also brings important security considerations. To mitigate risks such as data breaches and system vulnerabilities, it's crucial to establish a secure and controlled environment. Therefore, deploying a Python interpreter within the meta-prompting framework should be done in a secure sandbox. These measures are vital to maintain the system's integrity and protect user data, ensuring that the benefits of improved problem-solving efficiency aren't compromised by security and privacy concerns. Now, let's delve into the additional analysis of meta-prompting. The meta-model's dynamic selection of expert types clearly shows its adaptability and strategic alignment with specific task requirements. When we compare tasks with and without a Python interpreter, we see interesting contrasts in the model's choice of experts, influenced by the available tools and task characteristics. In scenarios where a Python expert is explicitly mentioned for code generation and execution, there's a noticeable preference for technical and computational expertise. For instance, in Python programming puzzles, the meta model often uses expert Python, expert mathematician, and several tiers of expert Python programmers. This pattern reveals a task-oriented strategy, emphasizing programming and algorithmic problem-solving. Similarly, tasks like Game of 24 and word sorting prominently feature expert Python, showing the model's tendency to rely on computational expertise when Python capabilities are available. On the other hand, for meta prompting without a specific Python expert, the range of experts used is more diverse. Tasks like geometric shapes mainly involve design and geometry experts, such as expert graphic designer and expert geometer, indicating a shift towards visual and spatial problem-solving rather than computational approaches. In sonnet writing, the meta model naturally leans on literary experts, notably expert poet and expert literary critic, emphasizing creative and linguistic skills. This pattern demonstrates the meta model's ability to dynamically tailor its expert engagement to the demands of the task, using technical experts for computational challenges and a varied range of non-computational expertise for creative or abstract tasks. Looking at the number of rounds taken to reach a solution, we find that the average number of rounds required to reach a solution in the meta model varies significantly across tasks, reflecting their complexity and specific nature. Simpler tasks, such as word sorting, 3.31 rounds, and checkmate in 1, 3.48 rounds, typically require fewer rounds, suggesting a more linear and straightforward resolution process, likely due to their clearly defined parameters. On the other hand, more algorithmically challenging tasks like Python programming puzzles average a higher number of rounds at 6.07, reflecting the nuanced and multifaceted aspects of programming tasks that require extensive interactions for thorough clarification and iterative refinement. The Game of 24 and multi-step arithmetic 2, with averages around 3.5 rounds, blend computational proficiency with logical reasoning, necessitating additional rounds for accurate and precise solutions. This observed correlation between the number of rounds and the task complexity highlights the meta model's proficiency and adaptability. It efficiently manages simpler tasks with minimal interactions while skillfully handling the complexities of more challenging and heuristic-based problems, ensuring precision and efficacy in its solutions. This performance characteristic is particularly critical in environments where efficiency and interaction trade-off are key. The meta model's systematic verification protocol strengthens the reliability and robustness of its solutions. Fundamental to this approach is the consistent practice of consulting an expert for validation before finalizing responses, a principle applied across diverse tasks. This method is further evidenced by the detailed interaction data. In tasks such as checkmate in 1, for instance, the meta model employs a two-step verification strategy. Initially, it consults an expert chess player to come up with a solution, followed by a critical verification from an expert chess analyst, ensuring strategic correctness. A similar approach is adopted in sonnet writing too, where an expert poet drafts the sonnet, and an expert poet reviewer or expert essayist reviews it, making sure that the solution adheres to the strict rhyme scheme. This unsupervised but rigorous verification process extends to complex tasks like Game of 24 and MGSM, involving both external expert consultations and internal reviews. By integrating this dual verification mechanism, the model significantly enhances solution accuracy and reliability, essential for real-world applications where precision is paramount. Meta-prompting enables the meta model to acknowledge the absence or impossibility of a valid solution or its inability to find one more frequently than other prompting methods. In 100 examples of the Game of 24, the model reports no solution 9 times with expert Python and 15 times without it, compared to the mere 2 instances under standard prompting. In checkmate, across 250 examples, it admits to no solution 12 times without expert Python and 10 times with it, a rarity in multi-persona and standard prompting. While there were always solutions, it is arguably preferable to abstain from answering rather than provide an incorrect answer. Typically expressed as, "no valid solution found," or more explicitly as, "there is no solution to the 24 game with these numbers given the constraints," these acknowledgments are likely the result of the model's verification and feedback loop, emphasizing accuracy and confidence over speculative but incorrect responses. Even without the enhanced capabilities of meta-prompting, GPT-4 stands out as an effective zero-shot task solver under standard prompting conditions. Its performance across various tasks, including Python programming puzzles and MGSM, is remarkable, particularly when compared to other LMs. GPT-4 excels as a task-agnostic solver, capable of processing and responding to diverse queries effectively. A significant attribute of GPT-4 is its proficiency in following instructions. Given clear and unambiguous natural language instructions, the model demonstrates a high level of compliance and accuracy. This aspect of instruction following is also a cornerstone of our meta-prompting framework, where we leverage GPT-4's capabilities. Our experiments reinforce that GPT-4 excels in code generation, demonstrates impressive zero-shot reasoning, and engages effectively in role-playing, solidifying its position as a versatile and reliable LM. In comparison to GPT-4, GPT 3.5 demonstrates a more limited scope of performance enhancement across various tasks. Although it shows notable improvements in specific tasks such as sonnet writing and checkmate in 1, its capabilities do not consistently surpass baseline standards or zero-shot COT prompting methods in other tasks, notably word sorting and multiple arithmetic 2. Our qualitative analysis suggests that GPT 3.5 may not be as effective as GPT-4 in simulating role-playing scenarios or managing extended context windows. This observation leads us to believe that factors such as the scale of the model, the quality and size of the instruction following corpus may be significantly influencing the efficacy of the meta-prompting approach. Furthermore, it appears that the advantages offered by meta-prompting may even emerge more prominently at larger model scales. Section Summary. The integration of a Python expert into the meta-prompting framework significantly improves problem-solving efficiency, as demonstrated by the increased success rates in Python programming puzzles, Game of 24, and word sorting. Real-time code execution allows for instant validation and optimization of solutions, resulting in higher accuracy rates. However, the deployment of a Python interpreter within the framework should be fortified with a secure sandbox to address security and privacy concerns. The meta model's expert selection is task-oriented, utilizing technical experts for computational challenges and a range of non-computational expertise for creative or abstract tasks. The number of rounds required to reach a solution varies across tasks, reflecting their complexity, and the meta model's systematic verification protocol enhances solution reliability. Meta-prompting enables the model to acknowledge the absence or impossibility of a valid solution more frequently than other prompting methods. GPT-4 demonstrates impressive zero-shot task-solving capabilities, excelling in code generation, instruction following, and role-playing. In comparison, GPT 3.5 shows limited performance improvement, suggesting that factors such as model scale and instruction following corpus quality may influence the efficacy of the meta-prompting approach. Section: Limitations and failure modes of meta-prompting. We're going to discuss some of the limitations and challenges we've encountered with our innovative meta-prompting framework. Despite its potential, there are several issues we need to address, including cost efficiency, scalability, the linear nature of operations, domain restrictions, information transfer difficulties, and response patterns. One of the main issues is the high cost associated with multiple model calls. In our setup, we use GPT-4, and the dual role of the meta-model and the experts, each with unique instructions, results in significant costs under the GPT-4 API pricing model. This makes meta-prompting less effective in smaller models like ChatGPT, which don't have the same capabilities as GPT-4. As a result, meta-prompting can become quite expensive due to extensive model interactions and long message histories. However, as the costs of language models decrease, these costs will also decrease. We should also note that recent OpenAI API features, such as the ability to run code in a sandbox directly through the API, could significantly reduce our system's costs. Another limitation is the need for a large scale and a large context window. GPT-4 meets this requirement, but smaller models like ChatGPT do not. Meta-prompting's design, which involves long message histories, requires a language model that can handle and retain a lot of textual information, a feature not all language models have. The linear nature of meta-prompting also poses a challenge to operational efficiency. The framework processes steps one at a time, depending on the outcome of previous calls. This limits the possibility of parallel processing, which could improve the speed and efficiency of the system. Our research also limited meta-prompting to a closed domain system. However, the framework could potentially incorporate external resources like APIs, specialized fine-tuned models, search engines, or computational tools. Future versions of the meta model could benefit from refining or summarizing its history before moving forward, which would improve the relevance and efficiency of the process. There's also potential in calling on multiple experts at once or using a single expert with different temperature parameters to combine their outputs. One practical challenge we faced is the meta model sometimes forgetting to convey necessary information to experts in the correct format. This can lead to confusion and highlights the need for better information management. Lastly, the meta model's response pattern often includes apologies, especially in tasks with lower performance. This is likely due to its training on instruction following data. Now, let's put our meta-prompting approach in context with recent advancements in prompting strategies and scaffolding techniques. Recent efforts in language model scaffolding and prompting methods have greatly improved the arithmetic and common-sense reasoning capabilities of language models. Methods like chain-of-thought prompting and its variants have changed the way language models process complex queries, encouraging them to think sequentially like humans. These methods break down complex questions into simpler subtasks and solve them systematically before providing a final answer. Recent innovations like tree of thought, graph of thought, program of thought, and skeleton of thought have further enriched this domain. These methods explore dynamic, nonlinear reasoning pathways, expanding the computational and heuristic capabilities of language models. However, they require more resources, take more time, require manual prompt crafting, and are often specialized for certain types of tasks. Recent instruction following techniques and data collection efforts have expanded language models' ability to follow instructions, mimic certain aspects of human behavior, and assist in tasks like annotation and evaluation. Language models like GPT-4, PaLM, and Llama can now effectively integrate self-feedback and refinement mechanisms through prompting. They can use their own natural language outputs to guide their behavior and improve decision-making. The integration of role-playing and self-collaboration concepts into language models has proven useful for enhancing their problem-solving capabilities and optimizing their domain-specific knowledge and expertise. Assigning expert personas or roles to instruction following language models improves the quality and accuracy of their output. Assigning multiple expert identities or roles to a single language model and prompting it to conduct multi-round internal dialogues can lead to more reliable and comprehensive analysis and more well-rounded solutions. There's also been growing interest in using language models for autonomous decision-making and task execution. Open-source projects like AutoGPT, AgentGPT, BabyAGI, and LangChain are developing agent protocols capable of planning, decision-making, and executing tasks end-to-end with minimal or no human intervention. However, these autonomous models could be exploited by malicious individuals and pose threats to humanity. Ensuring safety and security with these agents is crucial. As language models continue to evolve, the integration of external tools is becoming increasingly important. This allows language models to effectively engage with real-world scenarios and tackle a wide range of dynamic tasks. OpenAI's incorporation of predefined APIs and plugins into ChatGPT highlights the importance of external integration in developing a comprehensive language model ecosystem. However, most approaches often limit themselves to a select group of tools or domain-specific resources, posing challenges in adapting to new domains. Our meta-prompting approach treats the language model as an independent tool and expert, available on demand for specific tasks. Incorporating a Python interpreter to execute and evaluate model-generated code has been instrumental in enhancing both accuracy and efficiency in various tasks.